The last bit we want to look at with vectors is this idea of dynamics, or motion if you like. We'll look at this in far more detail in extension 2. Let's look at it now in extension 1, we touch on it, and the idea of resolving vectors, which basically is what we were talking about yesterday with projecting one vector onto another one. We're interested in dynamics problems with things that are moving, but they're not necessarily going to be moving horizontally or vertically. I mean, some things do, but a lot of things don't. So we like to then resolve them into horizontal and vertical, just makes the maths easier. Basically, as I was saying, this idea of resolving is projecting the vector. Let's just look at one dimension to give you an idea. So a plane's travelling south, velocity 100 kilometres per hour, experiences a tailwind of 25 kilometres per hour. What's the plane's resultant velocity? So there's our plane, down it goes, 100 kilometres per hour, and along comes the wind. Blows that, 25 kilometres per hour. So essentially we just add the vectors, and as a result it looks like the plane's going at 125 kilometres per hour. But that's if it's straight line. If it's at an angle, so let's put 2 dimensions onto it. Same problem, but now there's going south, but our wind is blowing sideways. So what would happen? We'd add those 2 together and it would look like the plane's going along that black vector there. Now we could do a bit of Pythagoras, we could work out, oh actually it looks like this plane's travelling at 103 kilometres per hour. So that's the basic idea. Force. When we're resolving vectors and dynamics, we don't usually talk about velocity and so on. It's the force we always start with, what force are acting on things. Now, force has magnitude and direction. This is why we can represent it as a vector. Here's a very simple one where we're saying, hey, we've got 3 forces acting on this particular particle. What would be the result of all these forces acting together? And essentially it's just saying, well, add these 3 vectors together. Oh, well, effectively it looks like it's going 11i and minus 3j. Oh, n, by the way, is newtons, the units for force. Okay, well, let's look at this one. We've got a tractor and it's pulling a barge along a river there. So effectively the tractor's pulling it at an angle of 400 newtons there, and the angle is 14 degrees. But what's it going to look like the barge is doing? What's happening horizontally? Well, it's like saying we're going to project that vector onto the horizontal one. Essentially that's what we're doing. So I'm going to project T, let's call it tractor vector, onto the B, the barge vector. We saw yesterday our formula, magnitude of T cos theta times I, we end up with 400 cos 14. The reality is, in a problem like this, I don't really need to use this formula, because all I do is I look at the right angle triangle and I say, well, which side have I got? Oh, I've got the adjacent side, so it must be cosine. And the angle, well, it's 14, it's got to be 14. And, well, 400 is what it's multiplied by, the hypotenuse. So I would normally just go, oh, well, that's 400 cos 14. If I wanted to work out the vertical component, I'd do a similar thing, but it would be 400 sine 14, because the side is opposite the angle. So it can be very quick to work out. You don't really need to use the projection idea, but that's where it's coming from. Oh, what's that work out to be? There we go. About 388 newtons. So let's look at this sort of problem then. We've got this mass on a smooth plane. I like saying smooth plane so it can slide. Angle 30 degrees. We have a force, friction, 15 newtons, going up the plane. Friction always acts opposite to the direction the particle's moving. So particle's going down means friction's going up. Gravitational force, which obviously is vertical. We also have this thing called a resultant force. Don't worry too much about these forces now. Again, we'll look at it in far more detail next year. But these are all different forces that can act on a particle. But we want to work out, it's sliding down, what would its acceleration be going down? And what is the reaction force? What would be the value of that? Well, I want to resolve things. I'm going to resolve down the plane. Instead of doing it horizontally and vertically, it makes more sense to resolve in the direction I'm interested in. And I'm interested in down the plane. If that upsets you, just turn your head 30 degrees. Okay. That's horizontal, that's vertical, not a problem. It's 5G that I'm resolving, so it ends up being the hypotenuse. Well, what are the sides of these? I've just got to work out where the 30 degrees goes in this diagram. That's using alternate angles, things like that, we can work it out. Turns out it'll be this one down here, is the 30 degrees. Okay, well once I know that, I can say, well, if I just now look down the plane, that's all I'm interested in. So down the plane, I would have the 5G sine 30, because it's opposite the angle, so that's going to be 5G sine 30, and minus the 15, minus because it's in the opposite direction, so it must be going in the negative direction, minus 15. Well, that tells me the force going down the plane. Force is mass times acceleration. Mass is 5 kilograms. So I know 5 times the acceleration, that's what I'm trying to find here, would end up being, bit of calculation there, 9.5. So the acceleration down the plane is 1.96. Also wanted me to work out this reaction force. Well, let's now look at the forces perpendicular to the plane. Now I have the reaction force going up, but I will have the component here of the 5G, but that would be cosine 30 because it's next to the angle. And again, they're in opposite directions, so one of them is negative. But I know the value of that force will actually be 0. Has to be, because it's staying on the plane. If it had some force to it, our block would be jumping up or something like that. Well, it's not doing that. So the forces must be in balance. Therefore, I know it's equal to 0. And playing around with those calculations, we can get the reaction forces 5 root 3 on 2G. I say, don't worry too much about a lot of the forces and what have you. This is more an illustration of what we could do, how we could use the vector ideas to solve these problems. Okay, so we'll have a go at some of these, 8F, see if we can make sense out of those.